the photoelectric effect. This is a concept that's part of Module 7, The Nature of Light, as part of the HSC physics course. And this is a concept which lots of students find often confusing, often cloudy. I'm going to try and make it as easy to digest as possible. I'm going to go back to the late 19th century. I'm going to start here. You had a range of different scientists, physicists who were experimenting with light and slabs of metal. There were scientists like Hertz, this guy here, who I can't pronounce his name, a German physicist, and you had Leonard, another German. Leonard, most notably, this guy here, Leonard, what he did was he used the following setup. So he had like an evacuated glass tube. Okay, so this was a partial, wasn't exactly vacuum. It was, most of the air was removed from the tube. You had two metal plates. This was all attached to a variable voltage source, and that was connected to a galvanometer. So here you've got electrodes, two metal plates, also called electrodes. So slabs of metal. And what Leonard did was this: he shone light of a particular frequency, particular wavelength onto one of the plates. And this plate here, this is called the cathode. This plate here. And this is called the anode. The cathode was negatively charged. The anode was positively charged. When light hit the cathode, electrons would be emitted and they would be attracted to the anode because opposite charges attract. These electrons are called photoelectrons. I've been asked this a lot in class. What's the difference between an electron and a photoelectron? All electrons in the universe are the same. Okay, they're the same particle. They're called photoelectrons in this case because they're electrons produced by light. Photo means light in Greek. So let me explain here. Electron, photo, light. So electrons coming from light, okay? And this is called the photoelectric effect. Because what was found was that you could get electricity from light. The flow of electrons, by definition, is electricity. The flow of charge, I should say. The flow of charge is electricity. You've got billions and billions of these photoelectrons being ejected from this cathode, the negative surface. They're making the way to the anode, the positive surface. And that gets measured by what's called a galvanometer. Now, galvanometer is a bit like an ammeter. It's not exactly an ammeter, but it's different in the sense that it can only detect very weak currents. It's highly sensitive, very small currents in units of, let's say, microamperes or even nanoamperes at times. But it's not as precise as an ammeter. Okay, it can only measure very small currents. So ammeters are used for large currents, galvanometers for small currents. So this is the photoelectric effect. Leonard could not theoretically explain what was happening, nor did any of the other physicists. Hallwalks, I think that's how you pronounce it, Hallwalks and Hertz. So there was a big question mark there. What was happening? How could you explain this theoretically? Classical physics, so the physics before the 1900s, for the year 1900, so that's the 1900, could not explain this effect. As I'm about to get into it now. So the person who was able to explain what was happening was actually Einstein in 1905. So Einstein wrote a series of papers in 1905. He called it his miracle year. One of those papers was on the photoelectric effect, and he actually won a Nobel Prize for that. Contrary to popular belief, wasn't his work on relativity that won the Nobel Prize, but the photoelectric effect. So he won the Nobel Prize in 1921 for his work on the photoelectric effect. And here's how Einstein explained it. Actually, before that, I'm going to go back to classical physics briefly. What the classical physicists were unsuccessful in was the following. They believed that by increasing the frequency of light, you should get more current. So higher frequency, more current. High frequency means high energy. So think of waves on a beach, right? High energy waves. So this is a way of thinking of how these classical physicists were thinking. High energy waves on a beach would move more pebbles off the sand, off the shore. You can think of it that way. So that's what they predicted would happen with the photoelectric effect. So higher frequency, higher current. Also, higher intensity of light, so brighter light, would result in electrons with higher kinetic energy. And also, light of any intensity and frequency will result in electrons being ejected, photoelectrons. The first one was proven incorrect, okay, through experiments like Lenard's experiments. Was not the case. Increasing the frequency did not increase the amount of current. Also, increasing the intensity didn't increase the kinetic energy of the emitted electrons, but it increased the amount of current produced. And the third was proven false. Not any current or frequency could emit photoelectrons from the surface of a metal. There was a specific cutoff frequency, a minimum threshold frequency that you need. So I'll get into the theory now. I'll get into Einstein's groundbreaking work on the photoelectric effect. Einstein began with the assumption that light consists of little packets of energy called photons. We didn't name them photons. This came later on by someone else, but he believed that light was made of chunks. So if you look at instead of a light wave, so the classical physicists were interested in waves. Einstein believed that you can break up this light into chunks. So if you were to zoom in, you'll see little chunks. These chunks, each chunk is called a photon, or more generally speaking, a quantum of light. Multiple chunks are called quanta. Quanta is plural for quantum. It's little packets of energy. In other words, light is quantized. So unlike Max Planck, who in 1900 proposed that black body radiation is quantized, only black body radiation, so heat, thermal energy, Einstein believed that light, all of light, so X-rays, UV, all forms of light was quantized. So Einstein generalized Planck's hypothesis. So Planck said that for every photon, every quantum has an associated energy E equal to HF. E is energy, measured in joules. Sometimes it's measured in electron volts as well. EV, electron volt. And 1 electron volt is equal to 1.602 times 10 to the minus 34 joules. H is Planck's constant, named after Planck, in his honor. Planck's constant is a very small number. It's 6.626 times 10 to the minus 34 joules seconds. And F is frequency with units hertz, named after Heinrich Hertz, in his honor. So there's billions and billions of these quanta striking a metal surface. Let's take a metal surface here. Let's say there's electrons here. Now it turns out that every metal has a specific property called the work function, phi, the Greek letter phi. The work function tells you how much energy you need to eject an electron from the surface, basically. So this was Einstein's picture. So consider light coming in. So light's made of quanta. I'm just going to draw a wave for now. Light of a specific frequency coming in, it can eject electrons from the surface. Okay, and you get photoelectrons. Each quantum of light has an energy E equals HF associated with it. Now, I should mention the F here should be a cutoff. Has to be light of a specific frequency. Not any frequency can be used. The classical physicists believe that any frequency of light can be used. That's not the case. That's not what was found experimentally. So they couldn't explain the experiments. The experiments showed what was happening. Classical physicists couldn't explain what was happening. So Einstein came along, used the idea of quantization, Planck's quanta, to explain the photoelectric effect. And to overcome this work function phi, you needed the energy to be equal to it, the energy of the incident light, HF cutoff, okay, the threshold frequency. This condition needed to be satisfied in order to eject a to have a photoelectron being ejected from the surface. Now, you can also have leftover energy. So if HF cutoff is greater than the work function phi, the photoelectrons will have kinetic energy. Okay, so this thing here, if it matches F sub cutoff, you'll be able to get electrons, a photoelectron released, but it won't have any kinetic energy. It'll just sit on the surface, right? Top of the metal surface. But if there's if the cutoff frequency is met, there's a surplus of energy, you'll have kinetic energy, or kinetic energy associated with the photoelectrons. So the kinetic energy, the maximum kinetic energy a photoelectron can have, is HF sub cutoff minus phi. Okay, that's the maximum kinetic energy a photon can have, right? It's whatever you start off with minus the work function, the energy they have to overcome. And what's very important here is that Einstein also used the law of conservation of energy in his explanation, because he believed that for every one photon, so a photon is given the symbol gamma, Greek letter gamma, for one photon, there's one photoelectron that's emitted, that's ejected. This fits in with the law of conservation of energy. I was asked this in class. It really makes sense when you think of it. A photon, particle of light, was basically light energy. Okay, it's light energy, and that gets absorbed. All of it gets absorbed by an electron. Okay, and the electron interprets this as heat energy, thermal energy. Okay, if you give light energy to an electron, it has more energy now. It gets excited, right? And that heat energy is transformed into electrical energy, or I should say, into kinetic energy, provided the light's strong enough. So the electrons are now moving. So I should better say just kinetic energy. So the electrons now have kinetic energy because they've got now light energy hitting them. And when there's lots of these kinetic energies, lots of these electrons, you will have a flow of charge, electricity. You can't have half a quantum, half a photon being absorbed, only one integer amounts of photons. So either 0 photons, 1, 2, 3, etc. But for every one photon that comes in, one electron comes out. Because there's so many photons, there's so many electrons coming out, there's lots of electricity coming out. Now, interestingly, if you were to go back to Lenard's setup, if you were to apply a reverse bias voltage, which means if I was to switch the charge of the plates from minus to plus here, and plus to minus, to minus, electrons emitted from this positive plate will no longer be able to reach the negative plate because same like charges repel. Negative electrons, photoelectrons, are repelled by the negatively charged plate. So no current is then measured, no electricity is measured through the galvanometer. And this reverse bias voltage allows you to calculate the kinetic energy of photons, of the electrons, I should say, as follows. We know from the law of conservation of energy that the change in kinetic energy plus the change in potential energy is 0. It's constant, in other words. If one goes up, the other one must go down. So you can rearrange this to get this. One is the minus of the other, basically. One goes up, the other one goes down. So you can actually calculate the change in kinetic energy of these photoelectrons by equating them to QV. If you go back to module 6, by definition, voltage V, there should be a delta here, but I've left it out, is the change in electric potential per unit charge. Rearranging this, for delta U, you get QV. And delta KE is half mVF squared minus half mV I squared equals minus QV. Change in kinetic energy is half mV sub F squared, so this is the final kinetic energy, minus the initial kinetic energy. And this voltage V is also known as the stopping voltage, V sub S. The stopping voltage is what prevents electrons from reaching the other electrode. So you can calculate things here using this principle of the law of conservation of energy. I'll make another video looking at graphs and whatnot and calculations, but these are the main ideas behind the photoelectric effect. I'll just summarize briefly. Observations of experiments in the late 19th century by these figures notably here, most notably Leonard, where he used this setup to detect, so to basically shone light of a particular frequency onto a metal plate, an electrode, and that released photoelectrons that created electricity that was measured using a galvanometer. And they predicted that if you increase the frequency, increase the energy of light, you would get greater current coming out. And that wasn't the case. And if we were to increase the intensity of light, you would get greater kinetic energy of the ejected photoelectrons, which is not true. You would actually get more current instead. And you can use any intensity and any frequency to get photoelectrons ejected. And that wasn't the case. There was a very specific cutoff frequency, a threshold frequency you needed. So Planck, going back to Planck, in 1900, he proposed that light, black body radiation, so a form of radiation, a form of light, is made of quanta, chunks of energy. Einstein took Planck's idea and he applied it to all forms of light. They were later called photons. So light is made of photons. It's quantized. It's made of chunks. Each photon has an energy given by HF. And each metal has a characteristic work function, specific property, a minimum amount of energy you need to release photoelectrons. And if you shine light with a particular cutoff frequency that meets the work function, that equates the work function, you get photoelectrons that are ejected. And if the energy is greater than the work function, incoming energy, you get kinetic energy. That's translated to the leftover energy is the leftover energy is translated into kinetic energy of the emitted photoelectrons. And through the law of conservation of energy, for every one photon, one photoelectron is ejected. And you can rearrange the law of conservation of energy to work out things like the stopping voltage and the kinetic energy.